This is Lab 5 on magnetic braking with Faraday by Julian Perez. The purpose of this lab was to observe a magnet falling through a conductive tube made of aluminum, and that was used to understand the effects of Faraday's law. The data taken from this experiment was then used in a computational model to re-examine this physical effect. Finally, the values computed with the computational model was then compared to the experimental values. The main physics concepts used were Faraday's law, which can be seen here, which relates the EMF in the tube to the amount of N loops in the tube and the flux passing through a segment of that tube. Using the resistivity of the tube and the EMF calculated with this equation, the current through the small segment of the tube can then be calculated. With this information, then the force acting on a segment of this tube can be calculated, and due to Newton's law of equal and opposite reaction, the force acting upward on the magnetic bar can also be calculated. For this experiment, an unused tube of aluminum foil was used. The tube's dimensions were as follows: 22 millimeters outside radius and a 12 millimeter inner radius. And the magnetic moment, which was calculated in the previous experiment, was found to be 0.843 joules per Tesla. To conduct the experiment, I dropped the bar magnet down the aluminum tube 5 times, and then also dropped it the same distance without the aluminum tube. I recorded myself all 5 times. Because of the short time span that it takes the magnet to reach the end of the tube, what I did was that I slowed down the footage to 8 times the speed. From there, I calculated the time that it took to reach the bottom. Then I took all the time that I had and I multiplied it by 8 to get the true value in seconds. After multiplying my values back to normal in seconds, these were the values I got. These values make physical sense, as the free fall, which was 0.25 seconds, took less time than through the aluminum cylinder, which was 0.37 seconds. Up next was the computational model, which involved simulating dropping the bar magnet down a conductive tube. The measurements mentioned earlier were used in this model to try to match it up with the real-life experiment. The following are the results of the 2 simulations of the experiment. One done where the magnetic moment of the magnet is 0 to simulate free fall, and another one done with the calculated magnetic moment of the previous experiment. The results show what would be expected, which is that the fall through the conductive tube would take more time. However, looking at the free fall, it took less time. This can be assumed because the fall does not take into account drag, which does occur in real life. As for the fall through the conductive tube, there seems to be a much longer time in the simulation. This is most likely due to an incorrect calculation of the magnetic moment from the previous experiment. The effects of very low resistivity of the conductor would be that the current produced within the tube would be incredibly high. This extremely large current would cause an extremely large force on the bar magnet. As the bar magnet begins halfway inserted into the tube and has a velocity of 0, as its velocity begins to increase, it would most likely not be able to increase to fall and simply hover at the edge. Cutting holes into the tube would result in the current being produced to not be symmetrical, or possibly not even being formed correctly at all, resulting in the force that is exerted on the magnet to also not be straight up. This could result in the magnet being pushed sideways and hitting the walls, instead of producing the upward effects that we assume in this experiment and in the computational model.